Hi, my name is Sako Lantin. I'll be your lab instructor for the day. We'll be studying 8 by serial in power out shift register. This is a very common part we can find online. We could buy it for $0.66. It has various interesting features. The maximum voltage for it is 7 volt. We could actually see it on the data sheet. It has inputs, 2 inputs, A and B, which are the first and the second pin. It has outputs, which ranges from 3 to 6, 13 to 10, and it has clocked and reset input, which is 9 and 8 and 9 respectively. The voltage, the ground is pin 7, and pin 14 is the V supply. So we are going to be testing the operation of this part, and we are going to see how it functions. So a little bit of a hint about what a shift register is. In this case, it accepts a serial in data and sends out power out data. So it reduces the time of data processing because it receives input at 7 clock pulse and sends output at just 1 clock pulse. So it has 7 outputs, basically 8 outputs. We are counting from 0 to 7, so it's basically 8 outputs. We can have a logic diagram of this, but before we go there, let's look at a basic diagram of it using, you see, we have clock. These are the clock inputs, and these are the power outputs, and this is the serial input, and these ones are the power outputs. So in our case, we are going to be using pin 1, which is A, as our input, and we use a voltage supply of 3.3 volt. We know that the maximum is 7 volts, so we can actually use more, but I choose to use 3.3 volt. So we're using 3.3 volt. We are going to connect pin 2, which is B, to 3.3 volt, keeping it actively high. For the reset, the clear, that is pin 9, we are going to connect it to active high, which is connecting to VCC. Another option is to connect it to the ground, that is active low. In that case, it resets every data, or it resets the content of a shift register. This is a symbol of a diagram of a part, sorry, and this is an expected waveform. This is the input, this is the clock input, and we have the first output. The first output comes on the second output. When the first, initially everybody is off, the first comes on while every other person is on. The second comes on while every other person is off. The third comes on while every other person, while the ones below is off respectively. And so you can see the shift in it, one after the other, like you have this shift of equal clock intervals. I used an analog discovery tool to display my waveform. I have it running. I have my supply of 3.3 volt, and I have my pattern generator on. I also have a logic analyzer on, which I'm using a positive clock, a positive clock on. So these are my inputs. I have this on the manual with instructions on how to connect it, even a step-by-step data sheet. So this is our circuit. Our circuit will look like this. We are using a push button, and we are using 8 LEDs to represent our outputs. We just want to display in a nice way to see exactly what we mean by a shift register when we enter one input and have 8 outputs. And the connection, this wiring connection, we have it on our manual, the step-by-step guide. So we have our device connected there. Everything is clearly explained. So when you press the operation, when you press the push button, if you notice it, when I press the push button, the first comes on, the second comes on, the third comes on, and I press it and I leave it off. So we are expecting, initially everything is off, and when you press, the first comes on while the other ones are off. So if I continue pressing, all of them comes on, and they maintain their current position, because remember we set the clock on high, so they maintain their high position. And when I let it go, then it goes off, it goes back to its initial position. But as long as I'm holding it, I have my high. So this is what we call a shift register. So we have it in this format. There are so many other way we could maybe modify it, using maybe like a transistor or stuff like that, to get it come back and forth. We could actually also put the clear to, instead of having it on a positive high, we could have it on ground to reset for it to constantly reset after a period of time. We could set a time for it to just reset after a period of time and comes back and off on. So this is just how basic our circuit is. So we're gonna increase the frequency. So I'll increase it to 5. When I increase it to 5 hertz, if you notice it comes on faster. The triggering time, it comes on way faster than when it was 2 hertz. So if we decide to like increase it up to, like, let's say 10 hertz, if you notice, if I increase it to 10 hertz, I have a more frequent. So you see, it's like almost, wow, you see, it just comes on so fast. So if I decide to bring it up to, like, let's really increase it, let's go to like 1 hertz. If I increase to 1 hertz, I'll just almost have everything almost on the moment I press it, because it's so fast, the speed is so fast. So that just almost like is steady. So yeah, that is the reason why to get a really good, we use a lower frequency to get it one after the other, get everything one after the other. And also you can notice that down here we don't have all our waveforms, and that's just because of our division. We could actually increase the division. I could increase it to like 30 seconds. If I increase it to 30 seconds, I will have all my waveforms. I'll be able to see my pattern on my waveforms, but it's so fast and so fast that we barely can see the clock pulse. And so to get like a view of the clock pulse, we kind of reduce the time. So when we reduce the time, we have a better view of the clock pulse, the first input and stuff like that. But the last one, since like the space is small for it, so we can see it. So this is more of what the lab today entails. So thank you very much.